Good afternoon, everyone. Thanks for coming. My name is Zenna Tavares. I'm an associate research scientist at Columbia University, and I'm a co-founder and president of Basis Research Institute. And today I'm going to talk about reasoning in various different forms. So this is the James Webb Telescope. It has 18 mirrors, 132 actuators, and it's allowed us to see far into the galaxies. So I'm sure many of you have seen over the last few months images produced, these wonderful pictures. But what interests me as a scientist is more about the minds of scientists. How is it that we can construct these somewhat magical devices? And one of the ideas that I follow is that there are some principles of intelligence that are kind of conveyed in scientists, but also conveyed in children. That there are some kind of key ideas which allows my friend's son to build this Lego piece that also allows us as scientists to understand how the world works. And so a lot of my work is trying to understand these principles and automate them in artificial intelligence. And in particular, one of the things I focus on is reasoning. And so today I'm going to talk about reasoning from three different perspectives. Knowledge representations, because reasoning relies on knowledge, algorithms for reasoning, and new kinds of reasoning. It's going to be a pretty high-level talk, but feel free to come and talk to me for any more details after the talk. So I'm going to start with knowledge representation and advances in knowledge representation, and I'll just show you a short video. Okay, so there's many questions we can now ask. How fast is this car going? Is this incoming car going to hit the purple car? And one of the ideas that I work with is that the way that we as humans can answer these questions is by having a model of the outside world within our own minds. So the basic idea is this. As a human, you have some kind of model of the outside world in your mind, and you can use that model to make predictions about the future. And that's useful because you can imagine how the future will evolve without the future actually evolving. We can also use this to plan. So if we're playing Jenga, for example, we can imagine what pieces to take before actually taking those pieces. And these models that we have in our minds, they don't have to be about just physics, they can also be about other people. So I can think about what you're thinking about, I can think about what you're thinking about, what I'm thinking about. Humans have this remarkable capacity to model the outside world and to use that model to make inferences about the future. And so this is not a new idea. Actually, if you go back several decades, one of the earliest kind of experiments into this was called like mental rotation. And so the experiment is this. So people showed participants images, so pairs of images. And the question they asked was, are these images taken from the same object rotated, or are they actually different geometric structures? And so I'll do this exercise with you. So I'll go through A, B, C. So raise your hand if you think that A is the same image, same object rotated, or it's actually a different object. Okay, what about B? What about C? Okay, I actually forget the answer, right? What they found is that if you plot the angle of rotation, right, so the magnitude of the angle of the rotation of the object, and you plot the amount of time that it takes people to respond, there's this very tight linear correlation, right? And so what that means is that, in other words, like the bigger the angle, right, the longer it takes for people to respond. And so the implication there is that the way people respond to this question is that they are basically mentally rotating the object in their mind. And so I'm sure probably you felt that you were doing that. And so here's some kind of scientific evidence that you are actually doing that. And so, in the kind of the intermediate years, we've been formalizing this idea in mathematics and computation. And one of the key ideas is the idea of a generative model. And so if you've heard of DALL-E or GPT-3, these are generative models in the sense that they can generate data. But this idea is quite old. And so there's many different kinds of generative models. So we can have what's called a probabilistic context-free grammar. We can have a graphical model. We can have something like DALL-E. All of these things, they generate data, often in some probabilistic way. And the thing that I focus on and our research focuses on is simulation models. And the basic idea is, as we just described, there is the real world on the left-hand side. We can build some kind of simulation model of that in the middle, and we can use that simulation written in code to make inferences about the future. Okay, so that's all kind of very, very familiar. But one kind of twist is this idea of a probabilistic simulation. So on the left-hand side, we have the normal code, right? So this is a kind of a toy simulation of some kind of driving scenario where we have some velocity, some height, some weight, and so on. And we can imagine doing some kind of time step simulation into the future. And the first thing that a probabilistic simulation does is it replaces some of the constants in that simulation with random variables. So distributions which reflect our uncertainty about the true value. So here I'm replacing the speed of the car, the velocity v1, with some distribution over v1. So maybe it's 60 miles an hour, maybe it's 59 miles an hour, and this reflects our uncertainty over the true value. So perhaps this is also very familiar. Maybe some of you have already done kind of probabilistic simulations. The key idea is this idea of inference. And so what I'm showing you here at the bottom is you have kind of these two things. One, I can add data, so I've got my observations, so I've observed the frames of video that we saw. But in particular, I want to compute inferences. I want to be able to do reasoning. And so I want to be able to say, how far should I believe that the car is going, given the images that I've seen? Or do I think the car's going to crash, given what I've seen? So how should we do this? So the mathematics that described how to do this is called Bayesian inference. And it's described by some laws, which I'm showing you here. And I'm not going to get into the details of what they are, but at a high level, they allow us to take a model, to take some data, and combine those to get a new belief about uncertain variables in our model. And so one of the areas that we work on are programming languages, called probabilistic programming languages, to automate this process of reasoning. And so there's kind of a growth of these over the last decade or so. Here are some of the most popular ones. And they are essentially programming languages with this feature of conditioning with evidence. So you write down a model, you write down the data, and you say, here are some questions that I have, and they automatically compute the answer. And so a lot of what we've been building on is using this as a foundation. So probabilistic programming languages, if you haven't played with them, here are some of the most popular ones. Pyro is part of our team. I didn't develop it myself personally, but many people in my team do work on Pyro. But we're thinking about what is next in the world of reasoning algorithms and systems. Okay, so I want to go back a little bit to this idea of mental rotation. So if you think about what's going on as a computer scientist, you might think, well, somehow I've got some kind of data structure in my mind, and I apply some operations to that data structure, and that's what allows me to do this kind of mental rotation. And thinking about data structures, they're very commonplace in programming. I'm sure everybody here has used sets and lists and stacks and arrays and so on. And just as humans in everyday life, we use these kind of structures mentally. So if I line up to get food, I'm doing some kind of queue operation in my mind. But if you look at machine learning, there's nothing like these kind of structures in modern machine learning. And so one of the questions that we've been thinking about is, how do we bridge this gap between this feature, which is a data structure, which is obviously very important to all of computer science, and machine learning, which seems to not have anything like that? So taking a step back, one way to think about this is an idea called levels of analysis. And this might be quite kind of familiar in some sense to computer scientists and programmers, but maybe the particular terminology you haven't heard of before. And so the basic idea is from somebody called David Marr, who was a scientist at MIT. And I heard this idea when I joined MIT, and the basic idea is that you can understand an information processing system at different levels of analysis. So at the highest level, you have what's called the computational level, and this is basically saying, what is the system trying to do? It's more like the spec. At the second level, you have what are the algorithms that the system is using to compute this computational goal? And then the third level is, what is the actual implementation? And that could be on the program and hardware, but it could also be on our wetware in terms of our brain. And the key idea behind these levels of analysis is that there's a kind of a many-to-one or one-to-many relationship. You can have many different algorithms which compute the same computational goal. You can have many different implementations which compute the same algorithm. And so going back to this idea of a data structure, we can understand data structures at a higher level than the particular implementation. And so one of the things that we've been working on is saying, well, what is a stack really? So a stack at the highest level is something which if you push to that stack and then you pop, you get back the same stack you started with, and you get back the same object that you pushed on in the first place. And so this is like the high-level algebraic law of a stack. But can we take that high-level law and turn it into something at the lower levels implemented using modern machine learning methods? And so I'm going to kind of skip over how we actually do it, but the high-level process is we take this kind of high-level law and translate that into a loss function, which we can train using machine learning techniques. And so what does that mean in practice? So what I'm showing you here is kind of this neural stack. So to be concrete, we've trained this push function, we've trained a pop function, both of which are neural networks, and we've trained this kind of constant empty vector. And so the first thing to see is that essentially it works as a stack. So I'm pushing on 8, 6, and 4, and I'm popping 3 times, and I'm getting back the same thing that I pushed on. The more interesting thing is the intermediate level, which is showing like how does a neural network represent a stack. And so if you look at, let's say, the fourth digit across, that's the internal representation of this neural stack after having pushed 8, 6, and 4. And if you look carefully, you can see it's somehow learned to interlace these different images so that it can then further pull out the information at once. So again, so this is a stack in any kind of real sense of a stack, but it's implemented in a very different way. You wouldn't know how to code this up yourself, but you can train it if you just try to adhere to the high-level laws of what a stack is. And we can do the same thing for essentially arbitrary data structures. So you take a queue or a tree, and if we can write down what it means to be that data structure at the high level, we can compile that into a loss function that we can train basically arbitrary neural networks to do. So this is kind of still early work, right? But we think is kind of the first really interesting approach which we can take to bridge this divide between data structures and kind of modern machine learning techniques. I think my screen is slightly zoomed in. Oh, there we go. Or maybe that's not better. I don't know. Okay. Okay, so the next thing I want to talk about is advances in reasoning algorithms. So this is Galileo's experiment where he's dropping two different objects to figure out if they fall at the same speed or not. And one of the things more generally that interests me is this idea of scientific discovery that I spoke about at the start. And in particular, the history of scientific discovery, all the way back to ancient times. And so there's been many different kind of theories and classes of theories, all the way from Ptolemy up to Newton through to modern string theory and so on. And one basic question is, what if we have all these different theories, what is the space in which these theories are instances of? Like, in other words, like, what is the type of the theory? And one idea that I find quite compelling is the idea that theory is a little bit like programs. In other words, like the space of theories is a little bit like the space of programs. And therefore, scientific discovery is a little bit like program synthesis. And so this idea of like using program synthesis, where programs are models and program synthesis is like theory discovery, has seen some kind of cool work in recent years. And so here are some examples by Kevin Ellis, by Faraz Saad, and some work that I'll talk about right now. Okay, so this is a system, kind of a video game system, and I'll just show you what it is on the right-hand side. So on the left-hand side, we have essentially a interface, some code and a language that we created called Autumn. And so this is a kind of reactive programming language. And on the right-hand side, we have an interface, and I'll just show you a very simple example. So I'm going to press play, and this is just compiling the code and running it interactively in the browser. And I'm clicking, as you can see, and essentially these blue dots are appearing and moving around. And so in having seen this, you probably already automatically formed a theory about how this world works. Like maybe it's something like when Zenna clicks, some kind of dot appears and it moves around randomly. And that is true, and that is kind of what this code on the left-hand side does. And so the problem that we're trying to explore here is how do we build a system that, like you, can observe these sequence of video frames and the actions that I did and figure out the program on the left-hand side. So from video and user input to program. And so to kind of build on my analogy, we think this is a little bit like science because you're observing what's happening in the world and you're trying to figure out some kind of theory underlying the behavior that you're seeing. And so in many ways, this is a very hard problem, and I'll just show you one example to kind of explain why. So let's show you 5. Okay, so here's an example, right? And so probably immediately you have some idea about what you want to try, right? So I'm going to click, and you can see some dots coming down. And so one of the really hard things is that if I click this kind of yellow thing, nothing happens. At least observationally. The visual world has not changed, but something internally in the program has changed, right? So if I click again, now a yellow dot is coming down. So this is hard for AI algorithms because the algorithm has to figure out that there's some latent or hidden state that has changed in response to what I've done, but has made no visual change in the world. And so you might think, okay, what's going to happen now if I press blue? Or you might think that it's going to make a blue point, but it does something different. And so this process of like building hypotheses about how the world works, also what experiment should I try to invalidate or falsify my experiment, is what we've been exploring in this very simplified domain. So visually it's quite simple, but it's rich enough to explore many of the interesting components of science. Okay, so how do you actually do it? That would be, many talks in of itself, right? But one way to think about it is that an interpreter or a compiler takes as input a program and produces as output the video frames that I saw. And what we kind of want to do is the inverse of that process. We want something which will take the videos that we saw and go backwards, in some sense invert the compiler or invert the interpreter to produce the program that produced it. And you can check out this paper, it's on my website, to see the details of how we actually do it. But this idea of inversion, right? So we can think about this, as I just said, inverting the interpreter is kind of program synthesis or model synthesis, and this idea of inversion kind of pops up everywhere when you start thinking about reasoning. So what do I mean by inversion? Well, I mean you start with some model, some function that computes, takes some input x and produces some output y. And more generally, that function is expressed as a program, and so I want to invert the program that computes that function. And so aside from the example that I just said, there's many areas and places in which this idea of inversion shows up. So one example is in vision, right? So the real world is three-dimensional, unlike the video game that I just showed you. But what we observe as humans are basically two-dimensional images. Your eyes observe two-dimensional images, and somehow your brain figures out the three-dimensional structure of the world from these two-dimensional images as input. And if you know anything about graphics, you know that we actually know as scientists and engineers, we know how to do the forward process. We know how to take a three-dimensional representation and do something called rendering and output a two-dimensional image. And that's what you see when you go to the movies, when you play video games. It's kind of a well-established field. But how do we do the inverse? How do we actually invert that rendering process and go from the image to the images to the 3D structure? Similarly, in robotics, we know how to write a forward kinematic function, and that takes the angles of the joints of a robot and says, where is the hand? But often we want the inverse. I want my hand to be in some target location. What should the joints be? What should the joint angles be? And so we're often in this regime where we have a forward model, but what we want is the inverse model. So why is this hard? There's many reasons why this is hard to do. The first reason it's hard is most interesting things are not invertible. So in the case of kind of this 3D example, I've got these two scenarios on the left and on the right. And in the right scenario, we've got this additional green sphere at the back, but it makes no difference to the image, right? Because it's occluded. There's something in front of it, right? There could, in other words, like there could be many things behind my back, and they would all produce the same perception for you. We don't have to go to something as complex as rendering to see this. If I just tell you that, two numbers, x and y, sum to 5, and I ask you what are x and y, well, it could be that x is 3 and y is 2, or x is 4 and y is 1. All of these are different possibilities. And so the addition function is the non-invertible function. And so the idea that I had, and this idea started in grad school, and we've kind of been continuing it since, is to generalize the notion of inversion with something I call a parametric inverse. Okay, so what do I mean by a parametric inverse? So let's take addition as a very simple example. So like we just discovered, addition is not invertible. But I can define this parametric inverse. And so this parametric inverse, f to the minus 1, takes in some value z and some parameter theta and returns two values, z minus theta and theta. The basic idea being that z minus theta for x, add theta, is equal to z, right? So if I put in z as some number, like 5, and then I choose theta arbitrarily, then I'll get out two values, one for x and one for y. And as I vary theta, I'll get back all the different possible combinations of x and y, all of which sum to z constructively. And you can do the same thing for the square function, right? F of x equals x squared. Again, in the inverse direction, there's two roots, but I can just parameterize that choice. So I get back the positive and negative root, in this case, where theta determines which of the roots I get. So that's, hopefully that makes sense, but by itself isn't that useful. The key idea is that we can apply this idea through composition. So if I have two functions composed, so I have f of x and y equals x plus y squared, I can think about that as the composition of the addition function and the square function. And so here's the algorithm in a nutshell. I'm going to take the addition function, I'm going to take the square function, I'm going to replace addition with its parametric inverse, replace the square function with its parametric inverse, and invert the order of the composition. Right? And so during that process, my claim to you is that results in a parametric inverse of the original forward composite function. So, okay, so why do we care? Well, we care because programs, despite being millions of lines long and very complicated, ultimately reduce down to a small number of primitive operations. And so if we can, through virtue of composition, define the inverse of composite functions, we can actually invert programs. So our goal, in a nutshell, is to be able to produce a system where you write down as a programmer your program on the left-hand side, and that could be an arbitrary program in whatever, whatever complexity you want, and then we just say invert, and we have some compiler process which will take that forward program and spit out an inverse of that program. And what our kind of theorem shows is that actually we can do this by construction. Now, again, this is still early days, right? And there are many technical challenges. One reason why you should be skeptical is that if what I'm saying is true, I should be able to just take your hash function, invert it, and steal all your Bitcoin, right? Which we know is, we know hash functions are not things that are easy to invert. So the story is more complex, and again, I can talk about this in more detail, but that's kind of the basic idea which we're trying to follow. So taking a little bit of a step back, a broader view is that like many modes of reasoning can be thought of as program transformations. So this notion of inversion can be realized as a program transformation. Another common one is automatic differentiation. So if you've done any machine learning, I can guarantee that it relies on automatic differentiation. And what is automatic differentiation? Well, it differentiates functions, but ultimately it's a program transformation. You write down some forward program which defines a real valued function, and this AD method constructs the derivative of that function. So taking a narrower, broader view, program compilation or program transformation is a little bit too broad. Many of the things that we care about are really kind of what's called a non-standard interpretation. And what that means is that you take some program with its original syntax and you give new meaning to that syntax. So in the case of parametric inversion, it's saying, well, my original program said add these things, and now I want to do the inverse of that process. And so there's this kind of growing set of tools which are allowing people to give new meaning to their programs. And when we say meaning, one of the ways that we formalize this in programming language research is through semantics. And so we have our program and our compilers, which I'm sure everybody here is familiar with, but there's something called the semantics, which defines the mathematical description of what your program actually is. And that's normally expressed in some kind of semantic rules. So this kind of funny looking lined expressions on the left-hand side. But what we want is some systems that can allow us as programmers to go in and change the semantics of our programs. And there's a growing kind of small industry of tools that are increasingly allowing us to do that. So JAX is one, which you may have heard of. Cassette is another one based in Julia. And Enzyme is the third one, which operates on an LLVM level. And so this is still a very nascent area, and we're quite convinced that the future of reasoning and inference will rely on advancing this set of tools that allow you to modify the meaning of your program from within the same programming language. And that's kind of some of the stuff that we're working on now. Okay, so I'm going to go back to my video as I talk about different modes of reasoning. And we can answer the question of, is this car going to crash, or will it crash? Okay, so it just missed. And so there's many questions we can ask. So one kind of question, which is not within the kinds of questions that I've spoken about so far. So far I've talked about inference, prediction, and so on. A different kind of question is counterfactual reasoning. So you might ask, would the crash have happened had our car been 20 meters ahead, right? Or had the incoming car been going 10 miles an hour faster? And so this kind of counterfactual reasoning is everywhere. Whenever you hear like a would or could question, this is kind of a counterfactual question. So here's an example from a few years ago where Mike Pence said, if the swine flu had been as lethal as the coronavirus in 2009, when Joe Biden was vice president, we would have lost 2 million American lives. Right? So this is a counterfactual statement, right? It's a little bit morbid now because we have lost almost 2 million lives, right? But so there's kind of a few different things to think about in counterfactual statements. So one is that they're kind of false by construction, right? It's based on a premise which is not true. But two, there's a sense in which you can evaluate whether it's a valid counterfactual or not. And I'll leave this to you to evaluate whether it is or not. Okay, but what is the counterfactual kind of mathematically or conceptually? Well, as a kind of a toy visualization, so imagine we have this model on the left-hand side. So this is our normal kind of model of how the world evolves. So we've got time on the x-axis and some kind of variable space on the y-axis. And so we've got these different possibilities of how the world might evolve. And in the middle, we've got what we called Bayesian inference before, where we add data to the system, we add our knowledge, and that constrains the possible worlds that could occur. So we're adding data. But a counterfactual is on the right-hand side, and that's saying, well, we've got our data, but we're also going to construct this hypothetical. And this is saying, well, what if something were different? So it's almost like a cut to the actual world in reality to describe what could have happened or what would have happened had something been different. And so one of the areas that I work on is sometimes called causal probabilistic programming, right? Where we take the probabilistic programming languages that we spoke about before, Stan and Pyro and so on, and we add some constructs for causality, in particular for counterfactual reasoning. And the basic idea is that these languages allow you to construct, in some sense, twin worlds. The real world, which is your original program, which you've conditioned with evidence in the way that probabilistic programming systems allow you to do. But two, they take that and allow you to construct interventions. And these interventions essentially copy the entire world, where this new copied world has the kind of the hypothetical that you're considering at that time. And they manage all of the details about how to do that for you. So you just, at a high level, you ask the question, well, what would have happened had something been different? And it automatically computes the answer for you. So the one I work on is called Omega, and I'll just show you some of the examples that we can do. So imagine you're kind of driving a car, and then you see somebody pop out, some pedestrian pops out from behind an obstacle, and unfortunately, you crash into that pedestrian. Now we can ask the question. The basic question is, to ask the question of, like, is the fact that we were speeding the cause of the crash happening? Or if you're a police person, you might want to ask and answer this question. And so the goal in this experiment was to take a single frame of video, in particular the image that you're seeing right here, and answer the question, had the car been going faster, would the crash have occurred? And to think about how we actually do that, well, we've got to take this image, we've got to go from the single image back to the three-dimensional structure of the world. So we've got to invert this rendering algorithm to construct the three-dimensional structure. We've got to figure out how fast the car is going based on some model of car dynamics, and figure out like when the driver would have stopped, given some model of like when people generally stop when they see a pedestrian. And given all of that knowledge, then construct the hypothetical. Would the crash have occurred had something been different? And so here's a few different scenarios, right? So there's the original scenario where we crash on the left-hand side. There's a second scenario in the middle, had the obstacle been in a different place. And there's a third scenario on the right-hand side, which is, what if the driver was going under the speed limit? So here are kind of the results. And so in this particular example, this left-hand side image is saying, well, had the driver been going slower, the distance ultimately between the pedestrian and the car would still have been zero. In other words, the car still would have crashed into the pedestrian most of the time, right? As you can see here, there's a distribution, right? Because all of these questions are probabilistic. In other words, go ahead.
If the driver were going like way over the speed limit, might the pedestrian have also been fine because the driver would be passing by the time they made it into the road?
That's slightly true, right? Right? And so the goal is that you should be able to ask this question at the level that you just asked it, and the system would automatically compute the answer for you. Okay. And so this is the particular intervention that we're asking. It's not like super fast, right? But it's a good point. On the right-hand side, we're saying that, well, had the obstacle been in a different place, well, actually the crash probably wouldn't have occurred, right? And so in some sense, you might blame the obstacle for being where it was, rather than the driver, but we can't generally blame obstacles for things. And so at a high level, that's the goal. The high level purpose is that you write down your model, you write down your question, and the system computes the answer for you. Another example we looked at was in kind of glucose modeling. So here we have a diabetic patient where we have different attributes, the glucose level in red, how many steps they've taken, whether they've eaten, and so on. And so this particular patient had a hypoglycemic episode, which means that the glucose levels went too low. And so the question we want to ask is, would this have occurred had the patient eaten a few hours before, right? And as we can see from the right-hand side image, well, actually, it wouldn't have occurred, right? And so here's the kind of question that a doctor might want to be able to ask. It all relies on the knowledge which is added to the system through the simulation model, and the goal of the reasoning system is to be able to automatically compute the questions to hypothetical and counterfactual questions. Okay, so taking a step back, there's kind of three axes which I've spoken about, right? Reasoning algorithms, modes of reasoning, and knowledge representations. And what we've been thinking about is how do we advance along these three different axes. And if you look at kind of the history of kind of computer science and AI, there's been a bunch of different advancements along these. And one of the questions that we're asking is like, what is the future, and how can we push in these three different dimensions? And so this idea of, well, one question is, okay, so what is this limit? Like if we keep pushing in these three different dimensions. And that's what we're informally calling this idea of universal reasoning, almost like a limit, maybe an unachievable limit of these progressions. And this idea isn't new. If you look back to some of the earliest kind of pioneers in computer science, this is Leibniz on the left-hand side, Alan Turing in the middle, and somebody called Herb Simon on the right-hand side. All of these people, they had this idea of a universal reasoning machine, universal calculator in different forms. And it's somewhat been lost to the kind of advance of modern machine learning, and one of our goals is to somewhat revive this ambition of a system that can perhaps match the ambition in which these people thought of. Okay, so what do we mean by universal reasoning? Well, we haven't got a precise definition yet, but it's something like this. Well, the first thing is that it's necessarily going to be approximate, and the reason it has to be approximate is that humans and machines are bounded by kind of space and time. We can only calculate so much within our heads, and the computer can only calculate so much. And so approximation has to be part of the picture, where we're willing to sacrifice perfection in order to get some answers, which may be good enough. And so what we mean by an approximately universal reasoning machine is essentially a computational language, so some language which we can express our knowledge and the problems that we want to ask, which is rich enough to express all known computational problems and all known forms of knowledge. And paired that with reasoning algorithms, is able to produce good approximations, good approximate solutions within kind of the physical constraints of time, energy, and maybe even money. And so Basis is a new organization, and our kind of reason to exist is to build this kind of universal reasoning machine. And at a high level, we do two things simultaneously. One, we build upon the foundation that I've spoken about in this talk so far, of causality, of probabilistic inference, of program discovery, and we try and advance along these three different axes in collaboration with domain experts. So we're a new kind of organization in the sense that we build collaborations with domain experts, both in hard scientific problems, going to what I said at the start, and also in societal problems in many different areas. Sorry about this cut off, right? But as I just said, one of the key components is to work with collaborators with real problems, right? Such that those problems can drive kind of the direction of the technology. And we're building this foundation based on reasoning. And so just to give an indication of the kinds of problems that we work on, one is what I just spoke about, this idea of automating scientific discovery beyond kind of the 2D simulation model that I just showed you into like the real world with robots. In other words, can we build a robot that interacts with physical devices in the real world, not with the goal of solving any particular problem, but with the sole goal of figuring out how this particular device works. So a kind of intuitive scientific discovery. More in the kind of the societal domain, we work with domain experts in New York to ask questions like, well, if we instantiate this new policy, what will happen in New York? What will happen to homelessness? What will happen to crime? And so this is interesting because if it's hard enough to model one person, like how do you model an entire city of interacting people in organizations and so on? And so we like projects which really drive, technology beyond what we can do at the moment, but also if we can achieve them, would have some kind of good societal benefit. And third, in purely kind of scientific domains, we work on like large-scale biological problems. Like how do we model a cell, or how do we model kind of genome transcription at levels that haven't been done before? And so at a high level, this is Basis, and we're a new organization, very much looking for collaboration. So if you're interested in this kind of thing, feel free to reach out. And here are some of the kind of esteemed collaborators as part of this. And I will end just finally on this last video. Cool. Thank you. Yeah, good question. So I think part of the answer to that we do have a good idea about, in the sense of one of the ways in which people try to quantify, well, one, we can use probability to quantify uncertainty, but in particular we can use notions of information gain, right? So I should do experiments which kind of maximize my information gain about the world, and that's something you can formalize quite nicely, using the relevant mathematics. What I think is hard to understand and is very much not so much explored in the academic literature is like the idea that our uncertainty is like relative to our current knowledge. So like if I just go back to this example, well, I showed you this purple dot and I showed you what happened with the yellow dot, and you might think, well, what's going to happen when I press the red dot, for example, right? But that presupposes the idea that this red dot is a button, right? Which it might not be. So somehow you have to be able to form hypotheses about questions relative to your current knowledge while also accepting the fact that your current knowledge might itself just be wrong. And so that is kind of a hard thing that I think about a lot, and I don't quite have an answer to yet. Right, so I would probably distinguish between complex and chaotic, right? So there are some, as you said, chaotic systems which are by design impossible to predict. But even then, I think a key component is abstraction, right? So I don't need, it'll be very hard to predict, where any particular person is going to be at any particular time, right? Let's say in 50 years' time. But I might be able to predict, the general population trends of different countries. And so some of the things which may be kind of hard, or in some cases actually mathematically impossible to predict, might become tractable when you kind of coarse grain a little bit and you ask questions at a high level of abstraction. And in practice, that's what everybody does in science anyway, right? You're always, I'm not trying to predict where every atom is going to be. I'm always coarse graining to some degree. So I think, in some sense, it's not an answer. Like some of these things are just hard at any level of abstraction. But I think that's part of the answer. Yeah. So there are. So I think one thing I want to stress is that I think in general, like an actual universal reasoning machine is probably impossible, right? So we're always going to be approximating. And humans have made certain approximations both deliberatively as individuals, but some of these are just baked into our biology, right? So we come into the world with priors about how the world works. I mean, I can take, if I took your visual system and scrambled the pixels randomly, it would be the same information, but you wouldn't be able to navigate anymore, right? So your perception is attuned to many things which are just biological. And so I think humans are probably the most general reasoning machines that we have. Some of the biases may be just kind of a quirk of our history, but there are just some fundamental biases and limitations that any agent will have due to constraints on computation. And you can understand actually many of the constraints that humans do have in these kind of rational, like resource rational terms, like what should an optimal agent do given that it has some constraints on what it can do in finite time and finite energy? Yeah, good question. One of the reasons I started Basis as an organization was actually around the George Floyd protest, right? So in that case, remember there was this conversation ongoing around defunding the police, right? And so you've got people on both sides. Some people saying, oh, it's crazy, if you defund the police, everything's going to go to mayhem. Other people saying the police have too much money, and so on. And one of the things that I found dissatisfying about that whole conversation is an entanglement of two different things, right? So one is a question of values, what kind of society do we want to live in? And the other is more like an empirical question, just what will happen, right? If we defund the police in some particular way. And so what I think is an exciting potential for this kind of thing is to somewhat disentangle these two things, right? So that we can argue about what values we want, right? But the questions about what's going to happen if we instantiate this policy is not our opinion of it, right? Maybe it depends upon prior knowledge, which is somewhat subjective, right? But it's there's a matter of factness about what will actually happen, right? And so I'm interested in can we bring to bear the set of techniques which are quite powerful, but so far have been kind of used in somewhat limited domains, right? You've all seen things like DALL-E and GPT-3, which are fun, right? But they aren't having that much effect on kind of the important issues. And I think there's this breadth of computational tools that can help us ask questions like, okay, what would actually happen if we defunded the police, to help us guide these conversations. In terms of like, I mean, I'm also interested in just like, cool AI stuff. Don't get me wrong. I love that stuff. But in terms of like risk, I mean, I think, yeah, all the risks that you would think about are real risks, right? If you can build things that can generally ask questions about taking optimal actions, they can use those actions to cause harm. And I think, thankfully, there's like a lot of work being done to think about these things more deeply. But I think most of the solutions are going to be societal, right? How do we build the social structures that encourage things used wisely, as it is for pretty much every other technology that exists at the moment? Well, the short answer is it doesn't really matter. We tried a bunch. We did it with a bunch. We did it with a convolutional network, a dense network, and so on. So it doesn't actually matter that much. Yeah. So one of the ways that, forget universal reasoning for the moment. If you just think about modern machine learning methods that are deployed in the world, in the current world, they're often trained in a way which doesn't take into account their impact in the world, right? And so that's fine if you're just running this thing on your local machine, but if Google puts out some new search engine, that's going to affect how people behave, right? And so the short answer is that an agent should take into account the implications of it being deployed. Like, it should take into account, like, if this system is actually operating in the world, at some scale, the world is going to change. And that world changing may actually be in terms of changes to itself, right? Or changes to kind of the people interacting with it. And so, like, mathematically, you can, in some sense, you can handle this, at least conceptually. In reality, it's obviously a lot harder, right? How can an agent reason about some, smarter, better version of itself? But yeah, it's a hard question. Yeah, so this is not my domain of expertise. You'd have to talk to my co-founder, but I can tell you one project we're working on, and that's like large-scale genomic modeling. So modeling basically ancient population changes through history, all the way, going in how did humans spread out from Africa, using this kind of massive data set of ancient genetic data that's been collected to make predictions about what actually was kind of the state of the world in kind of ancient times. And so, it's like a massive probabilistic model where we're conditioning on all this data which people have literally gone out and collected, many of which is thousands of years old, and it presents like a tremendous inference challenge. But as I said, like, the biological side is my co-founder's side, and so if you're interested in that kind of stuff, then I can put you in touch. Yeah. So we use programming languages to express our knowledge and to express the questions. So like I said, we have these probabilistic programming languages that allow you to express uncertainty, allow you to ask questions which are about probability, right? So how likely is some future event to occur? Like, what is the plausible values of these unknown variables? Then you have kind of counterfactual features which can be included, as I said, that allow you to ask these what-if questions, conditional evidence. And then you can think about what is the progression of that. Right? And so I could imagine a few different ways that might evolve. Right? So one way that might evolve is to say, well, actually, there's some finite set of things that we might care about. So we've figured out uncertainty, we've figured out causality for the most part, and maybe there's like 3 or 4 other things, and when we get them, we're done. Or it might be that actually the foundation is more like natural language, where kind of in some sense the space of things that you can talk about is unbounded. Right? And so one of the cool things about things like GPT-3 and so on, for me, isn't so much that they are smart per se, but it's more that they allow you to ask questions in such a flexible way. So somewhat individually, I've transitioned from thinking, okay, we've got this core, mathematical core, and natural language is just kind of like a noisy approximation of it, to thinking that maybe it's the other way around. Like maybe something like natural language should be the core. But I don't know how that actually works is a little bit tricky. Like, you want the kind of things that a mathematical language gives you. Like, you want consistency, you want coherency, But I think you also want the kind of flexibility that natural language gives you, and I don't think we know yet how to tie those two things together. If you do, let me know. Cool. Any more questions? Do we have time?